Welcome to the museum. It's great to see all of you here tonight. I'm John Holler, the CEO, and it's my pleasure to welcome you here tonight on behalf of our trustees, our staff, our members, our amazing volunteers, and everyone who supports the museum, including you. So welcome. Let me talk a little bit about this Revolutionaries event tonight featuring Rick Rashid of Microsoft Research and John Markoff. It's part of our Revolutionaries series. Major funding for Revolutionaries, as many of you know, is provided by Intel Corporation. We're delighted to have Intel support this series, which they're doing for the fourth year in a row. We have additional funding this year now from the William K. Bowes Jr. Foundation, which has just come on board providing underwriting support for the lecture series, and we're delighted to have the Bowes Foundation involved. We also have support tonight from Microsoft Research, so we're delighted to have them be supporting this event tonight. That decision was made long after we invited Rick to speak, but we're delighted to have that support. Now for tonight's program. We are continuing our look at everything that's happening in research labs throughout Silicon Valley, because some of the most cutting-edge research in the world is happening here. And this is the second in a periodic series which began in July with DARPA's Dan Kaufman. Other events that we'll be having in this series include talks featuring SRI, IBM Research, and Intel Research, and we hope to add others as we move along. But tonight the spotlight is squarely on Microsoft Research, which of course is here in Silicon Valley, but it's really all over the world, and it is led by Rick Rashid. Rick was employee number 1 at Microsoft Research in 1991. He now oversees 850 researchers working for Microsoft throughout the globe, and they in turn collaborate with some of the leading researchers, universities, scholars, and people doing cutting-edge work in technology and business, government, and the nonprofit sector. If you look at the things that Microsoft Research and Rick's teams are working on, hardly anything seems off limits. They tackle social computing, mobility, machine learning, search technology, security, human-computer interaction. Those are just some of the most interesting and important ones that caught my eye as I was looking at the work that they do. They work both in basic and applied research, and their focus, of course, is the future. Not just the future of Microsoft products, although that very much is central to their work, but if you know Rick and you know his team, they're looking at great social trends, the way that the world is changing, both because of technology and the way we influence the course of technology as humans. So we're hoping to get a peek at all of that tonight in this wide-ranging conversation with Rick. John Markoff of the New York Times is our moderator. John is often a guest on our stage. We like to have him because he does such a terrific job and he's so knowledgeable in this area. We've already booked John for a few more lab events in the coming months, and we're proud to have him back tonight. So please join me in welcoming John and Rick.
You know, I wanted to start, we're going to spend a lot of time looking forward, but I wanted to start by looking backward because we're at the Computer History Museum.
And we're old.
And we're getting older by the day.
My wife made this joke as I was coming here that I was going to be on display at the Computer History Museum.
Part of the permanent exhibition, I think. Well, one of the things that you did first in your career, actually before you started your career, that influenced me a lot, actually, was Alto Trek. And so I really wanted to start with the story of Alto Trek. I understand it as either the first or one of the first network computer games. You were a graduate student at Rochester. How did you get your hands on an Alto, and who let you do something fun with it?
Okay, well, I'll explain that a little bit. So I was in the group of sort of incoming first graduate students at Rochester. So Jerry Feldman, who was associate director of the AI lab at Stanford, he went to the University of Rochester to start their department of computer science. And he went out. He didn't obviously have a real admissions process that year, but I was a student at Stanford. I've been taking a lot of courses there. And so he approached me to say, you know, would you like to be in this first group of students? And Jerry had a lot of contacts with Xerox PARC. And of course, the University of Rochester had a lot of relationships with Xerox, because Xerox was a long time, participant, the university and Xerox were, had sort of interlocking directorates, in terms of the board of trustees and the board of the company. And so there were some good relationships there. And Jerry was able to leverage those good relationships to get access to 4 Xerox Altos. So Rochester was actually the very first place outside of Xerox Park, outside of Xerox proper, to have access to Altos.
Had you seen an Alto before you went to Rochester?
I had not. Well, I didn't even see one when I got there. We got our first Alto at the end of the first year I was there. Before that, so for the first year I was at Rochester, our entire computing facility consisted of a Bendix Logiport terminal and a TI Silent 700. That was our printer. And we were using the SumX AIM facility at Stanford, because Jerry was able to, again, leverage his old relationships to do that over the old Telenet, right? So this was, it was just barely computing, back then. And when the Altos came, it was just amazing. I remember that when we first unpacked the very first one, they had no instructions. I mean, they'd never really shipped this to anybody outside of Xerox at the time. And so there was nothing that really described, exactly what it would do. And I remember we turned the thing on, we put in the cartridge drive, right, which was, I think, 3 megabytes or something. It was about this big around.
Maybe 5, 3 to 5, yeah.
And we put that thing in, and we turned it on, and I typed something, and I forget what it was, and I think it was like, I started typing F or something, and it started going munge, 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 and putting up the names of all the files on the machine. And I thought, oh my gosh, I've just destroyed. Here's this, that we have one of these, it just showed up. And now I've done some terrible thing where I've initiated some command, and it's like deleting every file on the disk. This is not an experience a young graduate student really wants to have. But it was fun. It turns out it was doing something called F-Munger, for those Xerox aficionados out there. And all it was doing was just printing out information about the files, right? But I was just panicked. So we had those really early on, and that was a great opportunity for me to really be able to program them.
Now, there had been a Trek game that had been text-based that had been around in mainframe computers for a long time.
Right, which is
Why
Fortran.
Trek?
It was in Fortran.
Yeah. Why Trek? Was that?
I was just a big Trek fan. I remember at Stanford when I was a student there as an undergraduate. We would do dinner every night. In the dorms, we would watch the reruns of the Star Trek episodes. So, it was just a lot of fun for me. And Gene Ball was the graduate student that worked with me on Alto Trek. And we just, we wanted to do something fun. We wanted to do a game. Unfortunately, the Altos were so slow that you really had to do some unique things. So I had to write the whole, it didn't have floating points. So I had to write the floating point library in microcode in order to be able to do floating point. And then there were some things that were just too expensive. So I just couldn't take a square root, right? It was just way too expensive to take a square root. So I remember for gravity, I came up with the idea of using Manhattan distance. And surprisingly, you could put something in orbit, with Manhattan distance as your gravity, which I thought was really fun. I enjoyed that idea.
Was this a side project, or was this research, or was there?
No, this was just fun.
So this
is just a side project. I mean, we just were having a good time.
And did you were you treating this as a personal computer? Did you understand that this was a personal computer when you had it, or?
Well, I think the best way I would say is we were treating it as our only computer. I mean, we knew it was a unique resource, right? We also were just about that same time we had gotten a Data General Eclipse system, and so that was sort of our kind of server thing. That was kind of our central system, and then these 4 Altos were really our resource for doing development around the.
And were they tied together by an Ethernet at that point?
Yeah, we had an Ethernet tying them together. In fact, that was really the one of the fun things about Alto Track was that the old 3 megabit Ethernet had this feature which was promiscuity for so basically there was an 8-bit code for each machine on the network that you could set, right? So you could be any machine you wanted to be, and if 0 was broadcast, you could broadcast to everybody, or you had a specific number associated with it. And so one of the things I did for AltoCheck is I wanted to have the equivalent of multicast. I mean, multicast hadn't really been invented in quite that way yet, but I needed to have a way for machines to be competing with each other in a single solar system, but not bothering other machines, right? Because it would just, again, if you start bombarding everybody with broadcast, everything would slow down, because processing Ethernet packets was a lot of work for these little machines that had very slow instruction sets. So I basically took the top 16 addresses and I made them the 16 sort of planetary clusters or galaxies or star systems that we had. And so whenever a ship went into one of these systems, it used that address, that Ethernet address. So the funny part of that was that eventually the game, everybody loved it. We played it a lot. Eventually it got imported back to Xerox PARC, and people really loved playing it.
Which
there.
was where I saw it.
You probably saw it at Xerox. So everybody enjoyed playing it there. It was a lot of fun. But they didn't actually know how it worked, right? And of course they had lots of Altos. We only had 4. They had lots of Altos. And there were Altos in those addresses, okay, that were being used. And so, as the story was told to me, when it got to be like 5 o'clock or something and everybody was starting to play instead of work, and that's the story I was told, at least. They might have played all the time. But there were certain machines that would just slow down terribly, all right? And no one understood why. And eventually, I think either I told them or somebody explained to them how the thing actually worked. So amusingly enough, a few years later, I became a professor at Carnegie Mellon University, and as I arrived, they were getting their first Altos. So this is the fall of 1979, but they did have a manual by that time. MIT and Stanford and Carnegie Mellon were giving little manuals describing how these things actually work. And in the description of the Ethernet, I remember seeing that the top 16 addresses were documented as reserved for Trek. Okay? So I thought that was great. So indirectly, I invented multicast for the Ethernet. Very indirectly.
One of those stories we'll get to. You didn't study computer science directly at Stanford. You studied math and comparative literature.
Right.
And I began to wonder, so you were also a Star Trekkie even at Stanford. Did you come to Star Trek via science fiction, or did you come to science fiction via Star Trek? What was the inspiration?
I was a science fiction fan from the time I was a little kid. I read the Mushroom Planet books, back in the old days. And there's a fan. I read, I think anything that looked like science fiction, Asimov, Heinlein, anything, I just absorbed them. Okay. I would read them so fast, it was hard. I would just sort of park myself in the library because it was just hard to get past.
But you didn't major in computer science.
There was no major in computer science.
In the late 60s, I think it started.
No, there was no major in computer science until after I left, for sure. I'm not sure what year it started. There were courses, and I took a bunch of courses. So I took a lot of computer science courses, so I had probably the rough equivalent of what would have been an undergraduate computer science degree too, but we just didn't have one. But comparative literature I got into because I was a foreign exchange student in Italy for a year, so that got me into literature and other languages, and then mathematics was always something I enjoyed.
Okay. And do you remember the appearance of this, what turned out to be the world's first video game in the Rochester Union, which was called Galaxy Game? Had you discovered Space War before? Does that ring a bell at all?
Yeah. No, I played it. Yeah. it was in the coffee shop.
Yeah.
Right. I played it in the coffee shop. That was just a lot of fun.
Was it influential in any way in sort of shaping your?
Well, I don't know if it was influential. I mean, certainly it was probably the first time I'd seen, a sort of reasonably sophisticated game being played on a computer. There were also, some of the MLACs and some of the other devices that were on campus, people would use them for playing games, or watching TV or doing there was a lot of things being done up at the AI lab or in Polya Hall, right? That were fun.
Did you discover the AI lab as an undergraduate?
Oh yeah. No, I would go up there because, again, I was taking a lot of courses and I got a chance to get up there and see that.
Would you have called yourself a hacker at that point in your? In the white hat sense of the
Well,
term.
I mean, in those days, I think everybody liked to think of themselves as hackers, right? That was the term we used. I really, to me, what was really fun was and the reason I got excited about computer science was this sense that, here was my intellect really animating this piece of metal, right? This device. I remember I took an architecture course. It was the second course I took at Stanford from Forrest Basket. And we had these 2116A and B machines that were sort of tucked away in a corner, in the quad. And you'd have to, usually I'd have to get them access to it at night because they'd be used all during the day and stuff. And so there were only, you'd have to compete with all the other students and people that were using it. And I just remember the very first time I was able to read a paper tape, sort everything in memory and write it back out on an ASR 33. I just thought this was like, I floated. It was like midnight when I got my program running, and I just literally floated across campus, back to the dorm room, because it was just so exciting. To me, it was so visceral. And I think that's really why I wound up going into operating systems, right? Because I just love the working at this very low level, working at the hardware.
And were operating systems your focus at Rochester? Was that sort of?
That was, I mostly did operating systems work. So if you look at as I was a graduate student, a lot of what I did, we developed something called the RIG operating system for Rochester Intelligent Gateway. We published a number of papers on that. So a lot, and certainly a lot of the ideas that eventually became important in my work on accent and mock, they all came out of the work I did, when I was in Rochester, as I was developing my ideas of how I would structure that operating system and how it would function. But I did a lot of other stuff as a graduate student. I also did a year of clinical neurolinguistics, working at Strong Hospital. I did.
Your graduate thesis was on computer vision.
I did. It was in motion computer vision, right? So I worked on something called moving light displays that were these moving images where you put points on a body and move it around, and then you can reconstruct the three-dimensional structure of the object. So I tended to work on things that I enjoyed and things that I had fun.
You went from Stanford, arguably the best weather in the world, to Rochester, which was that a shock to you? You'd been in Iowa, so you knew about real weather.
I was born and raised in Iowa. Nothing is really going to be a shock after that.
So
I always tell my kids about how I would walk uphill both ways, back and forth to school, and how I'd walk. Literally, my mom, we couldn't afford boots, right? So she would wrap newspaper around my legs and with rubber bands to walk through the snow to school. So after that, Rochester was a piece of cake. Although there was that blizzard of 1977 that was pretty impressive.
I wanted to ask about what led to mock. What were the roots of mock? Why?
Well, the mock operating system really came out of ideas that go back to the RIG operating system work that I did when I was at Rochester. So, RIG was the first time. I actually remember as I was sitting in the student union, and I started to realize that there was that I could build this relationship between message passing and communication and memory management. That those things could be thought of as duals of each other, and that you could think of them as being the basis for a set of primitives for an operating system. And so, the data general eclipse that I actually implemented that on was, really not, it didn't really have a full memory management system and paging system. But, when I went to, CMU, there we had, again, an early machine, the Three-Verse Corporation PERC, and I could microprogram it to do anything I wanted to do. So I designed an instruction set and I wrote the microcode so that it could provide all the facilities I would need to have, a system based on a very small set of communication and memory primitives that then I could, layer on top of. So in some sense, the original ideas came from my original work at Rochester. I refined them and really, came to understand what they meant and how they function with the work on accent. And then Mach was in some sense, the 3.0, right? How people always say it's always the third version. The first version is the one you had to do, but you shipped it early. Okay. The second version was what you thought you what were going to do in the first one, but you don't have any feedback on how it was really going to work out. And the third one is you really understand what you're doing. And I think for me, my 3.0 was Mach.
I want to ask more about Mach, but before I go further, what predisposed you to math from your family? Was there something that...
For my family?
Well, yeah, was it family or was it something else? Was there what?
Well, my parents didn't go to college, there wasn't, my dad was really good with numbers, but that's,
But do you think that was a possible influence? Did you have that?
I don't really know. I must say, I think the reason I got into mathematics was I went to Stanford, and, I got in the, first year math course there, and I just had a blast. And, after that, the second semester I got into the math honors program, which was just a huge amount of fun. And we had Professor Manham Schiffer that was teaching that particular course. And he had this philosophy of, if I haven't said it in class, it's not true, right? I have to prove everything from the beginning to the end. And, I just learned to love math from the way he taught.
So I was thinking on the way down here about how your software is probably in every device I use, and how ironic that is in some ways, as a Mac person. And I was wondering if Steve ever tried to recruit you.
Not sure exactly the right way of saying that. He certainly wanted to hire me. Recruit me is a different issue. I mean, he wanted to pay me. And I think either consultant or something, and, those days, my philosophy when I was at Carnegie Mellon was that I didn't, I did consulting work for companies from time to time, but I would never do consulting work about my work on operating systems, because my feeling was that I wanted to have, I didn't want to have any perceived bias in who I worked with or what I was doing, because I wanted everybody that I could talk to use what I was doing, mm-hmm. and I didn't want them to feel like I was beholden to somebody else, right? So we work with Apple, we work with Next, we work with Intel, we work with Digital, we work with the Open Software Foundation, just anybody. I was willing to talk to anybody and share my code with anybody.
And then when Avi Tavanian actually did go to Next, did he talk to you before? Did you give him advice on whether to go to Next, or?
I don't remember giving him advice. I mean, I think it was a good job opportunity for him. I mean, he finished his PhD. He was a great student, really super smart. And, he'd obviously done a lot of the implementation work on Mach. And I think this was just a huge opportunity for him, and he took it.
Yeah. Before going on more with technology, I wanted to sort of ask a general question about the relationship between entertainment. So we started with your work on Alto track, and just the relationship between entertainment and the advance of computer science, and if there is anything more than sort of random interaction, or whether computer science has been driven forward in a meaningful way by the entertainment world.
Well, I think there's always been. I don't know how you want to describe it as being in a meaningful way, but I think there's always been a lot of interest in how computers can entertain people, and I think a lot of the early people that I knew, certainly, that got into computer science, they enjoyed playing games on the computers. They enjoyed writing games for the computers. Whether they were text-based games or whether they were, later on graphical games, whether it was things like, moon landing or, missile command or any whatever you were interested in those days. And I think that, it has certainly, as gaming has gotten more interesting and more sophisticated, it has brought advances. I mean, you look at a lot of the work that's gone into, 3D graphics and making the graphics better. Well, that has gone hand in hand with the use of graphics in games, and the fact that, there was a lot driving, the development of better graphics boards as people wanted to have more games and better experiences. So I think there is a relationship, and there's always been a sort of an entertainment and education component to using computers.
What persuaded you to leave academia and go to Microsoft?
It was interesting because it was kind of I would sort of characterize it as a hard decision. And in fact, I was being recruited by Nathan Myhrvold at Microsoft to start Microsoft Research. And he worked really hard for a number of months. And I would keep telling him no. And the reason I would keep telling him no, I was, in a sense, I sort of felt a lot of loyalty to Carnegie Mellon. I'd been there for 12 years. I'd been very successful there. And, and also I was feeling kind of torn too because of the people that I knew there. And they had some expectations. There was at the same time Microsoft was trying to recruit me to start Microsoft Research. The university was trying to recruit me to be dean of the school. And this was also a period during which, as our Alan Newell, who's at CMU, one of the great, founders of that department, he was dying of cancer during that period. And he was one of my mentors, one of the people I really looked up to. And I could tell, and we had a number of conversations, that he really wanted me to stay. I think he was thinking about, he wants somebody to be there for the next generation, right, from the people that he knew and that he trusted. But I will also say that Alan gave me just incredible advice about, what I would need to do when I did go to Microsoft. And I really look back at that time as being, really seminal in terms of formulating, the way I thought about what I would do as I started Microsoft Research and really taking Alan's advice to heart.
Was the charter that Nathan held out to you creating something like one of the, were you trying to create a Bell Labs, or were you trying to create an IBM Research or a Xerox PARC? What was your mission when you went?
Actually, I was trying to create a Carnegie Mellon computer science department, in a company. That was literally my model. And if you go back to even the talks I gave in the early days, I always said that. My model was, I was, I'd been sort of, raised, at Carnegie Mellon as a professor, and that was my model for how you did, cutting edge computer science. Obviously CMU always had a strong relationship to industry as well. Going back, many years. And I always felt that was a great, the way the department ran, the sort of egalitarian structure of the department, the lack of bureaucracy, the reasonable person principle, all of those things were, to me, sort of how I thought, you should run a computer science department. And, and when I went to Microsoft, as I was even being interviewed with Bill, and with Nathan, that's why I said, look, if I come here, that's what I want to do. I want to create something that was like what CMU was like, but do it in the context of a software company where the output of that entity could go directly into products and really could make a big difference. So really that was my mental model. And honestly, I didn't know Bell Labs. I knew some of IBM Research, but I didn't know Bell Labs all that remarkably well. So I wouldn't have been able to use it as a model.
But now the institution you've created is so much beyond the notion of a computer science department. It spans many of the world's continents. It does things that are short term. It does things that are very blue sky. It's beginning to look like a Bell Labs or an IBM Research, to my mind.
Or a university. I remember I was meeting with I think the president of Brown, and I was pointing out that we had more PhDs than they did at Brown.
Is the number 850? Is that?
Yeah, we have about 850 PhDs. The total organization size is about 1,100. But it's been interesting. I think partly what's happened is that and I think of this more as the growth of the field of computer science. Microsoft Research has grown and it has expanded the number of areas in which we work, but that's really a reflection of the fact that the field of computer science has just changed dramatically, in the last 20 years. And it has grown to encompass a lot of other fields, or at least to reach out into a lot of other fields, right? So where we do work, for example, we do work in AIDS research and looking at new kinds of vaccines. We look at things like malaria. but we're looking at it from the perspective of how do you apply machine learning, right, to tackle those problems? How do you apply computer vision algorithms that were designed for one purpose to attack another kind of recognition problem, in looking at certain kinds of genetic structures. So I think, what's happened is that as the field of computer science has grown, we've grown to go with it. And also Microsoft has grown. I mean, the company is nothing like the company that it was when I started. I mean, we now reach into so many different areas. We've grown, 8 new billion-dollar businesses just in the last 10 years. And we're reaching out into home entertainment. We're reaching out into enterprise. We've got, the huge cloud infrastructure. More and more we're doing end user devices, although the company actually, even in the early days, did end user devices. So I think it's just been just a change in the whole industry over a period of time, and we've just been part of that.
Could you pick apart R&D? I mean, there is R&D. Your R, do you shade into D? And what about the numbers? I mean, I see numbers for R&D, and what fraction is R of R&D?
Well, so Microsoft spends something like $10 billion a year in R&D, but that's a description of what we spend to create our products, and that's what is normally described as R&D in the computer industry is what do you spend to create the new products that you produce. And again, within the technology field, that's most of what you do. It's not like we have huge physical plants in a software company, that we invest in. We're investing in people, and we're investing in the things, the software and the technologies that we create. Ours is a very small fraction. So if you look at it from the, total perspective, our PhD researchers represent about 1% of Microsoft's total workforce, and about 2% of the technical workforce. That's still a lot. I mean, that's a lot of people to devote to basic research, but it is a small fraction of what the companies otherwise spend.
Yeah. So how do you decide? So if you're going to take on a big new area in research, what goes into that process? I'm trying to think of an example. Is there a recent new large initiative that is sort of longer term that comes to mind?
Well, I think what happens, the way I look at it isn't so much like, I don't think of how we, attack, the future as saying, what are the initiatives that I create that somehow, cause things to happen. The way I look at my job is I hire really, really great people. Right? And we try to hire the very best people that we can. And we are, in many ways opportunistic in those hires. I mean, there are times when you will suddenly have a really great person, and you didn't think you were going to be working on that. And, you just really want to hire this really great person, and now suddenly you're doing another area of research that you weren't thinking of doing before. And so the way I look at my job is the most important things I do are to help determine, who we hire and who we fire, right? Who is our workforce? I mean, who are those really top people that are going to be, pushing the state of the art? And we let them figure out what they're doing. And they will individually take initiatives, or in groups, will take initiatives and tackle new areas. But for example, when, David Heckerman, and Nebosha Jolik started working, with the AIDS community, I only found out about that at lunch one day. I eat lunch in the cafeteria, sit down with different groups, and I was sitting down with David, and he was starting to explain this thing they were doing. And I think I remember my reactions being, oh, that's interesting. I didn't realize we were doing something like that. That's interesting. But then that's led to not just, a significant number of significant impact in terms of the AIDS community and the medical community, but also it's had an impact on the field of computer science because, he and his team, as they've been doing this work, they've been developing new machine learning algorithms and understanding how to apply them to sort of other more traditional areas of computer science at the same time. So I guess the way I would say is that, I look at our different research groups, and they each one are pushing different areas. They're each one taking initiatives in different things, whether that be in, machine learning or Bayesian inference or, deep neural networks, or whether it be in areas like, finding the relationship between graph theory and statistical physics and case satisfiability, right? That's another area we've pushed in. If you look at some of the work we've been doing in programming languages and program analysis, it's just been amazing. And, if you look at the most recent version of Microsoft Office that's just being released, Office 2013, there's a feature in Office 2013 called Flash Fill, where you basically sort of give the system an example. You've got some columns in a spreadsheet, and you make some other columns, and you put a few examples of what you want that column to be, and what happens is there's actually an automatic program generator built into the system that will create a program that is optimal to produce that output from the inputs that you specified. And then it will then use that to automatically fill in the other columns.
And it came out of the program verification world?
And it came out of the program verification world.
Running backwards?
It's like running backwards, right? So if you think about program verification, you're trying to prove properties of programs. So we've been doing that now, a very large scale within Microsoft for the last, really 13 years. This is really going the other direction and say, if I have a set of primitives and I have examples of what I want the program to do, can I write a program from those primitives that would do that?
You mentioned the important aspect of bringing the best people to Microsoft. I was just wondering if you felt guilty at all for bringing Peter Lee. He was halfway through his DARPA tour of duty, and you were good enough that you managed to get him to sort of drop it and come to be the manager of Microsoft Research in Redmond.
I think that's a higher calling. Honestly, I think in some sense, I never feel bad about hiring a really great person, because I think we have an environment where really great people can do extraordinary things and can change the world in a significant way. And if you ask Peter, I think he'd probably say that's why he came to Microsoft, because he really wants to change the world. And that's why I went to Microsoft, because I felt that, if I could be successful in creating this kind of fundamental basic research lab in the context of a software company like Microsoft, that we could do things that other people weren't doing, and again, I think that's what gets me excited.
And was there a point were you always the head of all? When did you make the transition to your current position?
I've always been in my current position. But they just keep changing my title. I started out as director of research, and then I was vice president of research, and then senior vice president of research, and I'm chief research officer. Okay. It's the same job.
But
right?
You never replaced Nathan at Mirvold at some point, did you?
No, because I never had. Okay. Nathan's job didn't quite exist by that time, okay. Right? So basically, Nathan ran something called the Advanced Technology Business Development Group when I first got to Microsoft, of which Microsoft Research was part. And probably the closest analogy to that today would be the Advanced Strategy organization that Craig Mundy runs.
Yeah.
But really, Microsoft Research has always been sort of a separate thing. So my joke about that is that I'm the Microsoft executive that's been doing the same job for the longest time. 21 years is a really long time, especially in corporate America.
Yeah, it is. So incremental innovation versus disruptive innovation. I knew the guys who basically in research who created, I don't know if it was your first, but the previous tablet product from Microsoft, and it never was a big. It got out into the world in very sort of siloed ways. It never sort of had a broad consumer impact. And I know that at the outset they had much broader vision. And I just sort of wondered about your sense about that, the evolution of that product that went from research out into the product line, and it didn't disrupt.
Well, I think that, again, to some extent, whether a product does or doesn't disrupt an environment sometimes depends on the time, right? When it's the right time, what is the right form factor, what is the right way in which you present it. I think there was a huge amount of innovation in the original tablet PC software. Chuck Thacker, was the person that actually did the original reference design for that. And he, of course, designed the Xerox Alto as well, and recently won the Turing Award. So I think, it's, there was a lot learned through that product in terms of inking and how the inking worked with the rest of the system. And a lot of those learnings have moved their way into other, our current products and other things that we're doing. So, you have to kind of look at each area. I mean, something like Connect is a good example where there is a set of technology, coming out of machine learning and computer vision, and then, having a really disruptive effect. Interestingly enough, it had a disruptive effect on the sort of game console business,
Yep.
and had a huge financial impact for us, very positive financial impact, and really has kept the Xbox as really the leader within that space. But even more interestingly, what Connect did is it's changed everybody's ideas about how people interact with computers. Right? So you've seen, once Connect came out, suddenly there was this sort of sea change in attitudes in universities about the research that people were doing. And everybody wanted to work with Connect, or they started thinking about other kinds of ways you could use gesture, other ways in which you could use vision, or other ways that you could use these kinds of technologies, to be able to have the machines interact with the person. And I think, sometimes, again, in this case, I think the timing was really right. I mean, whereas the tablet PC didn't, it was still basically a PC that now just had a new input mechanism. With Connect, you reached a point where suddenly you had a different relationship with the computer or with the game console. I remember when obviously, you could probably guess that we would be on the beta, in my family. And I've got 2 young boys. They're now 12 and 13, but obviously, now I'm talking about a few years ago. And I can remember bringing the Connect home and having them start to play with it. And I realized what a tremendous change that was and what a big hit it was going to be when I saw that one of my sons was having just as much fun celebrating, because the character on screen celebrated the same way he did, right? When he jumped up and down and celebrated, it moved too. And I realized that his brain had made the connection between him and the character on the screen. That they had suddenly become the same entity. And that he was feeling it that way.
Cyberspace.
Right? And at that point I realized, we've really got something, right? That's a big change in your relationship with the computer system. And so, and again, when do these events happen? In the field of computer science, you get these kinds of changes at different points. And sometimes it's the right time, or it's the right circumstances, or suddenly, the price point has changed, or people's attitudes about a technology change, and that'll cause something to take off. From my perspective, from the research environment, we just keep pushing the technology out. Okay. It does take. I mean, it does have that impact.
You're focusing on Connect and interface, but where I've seen it, where there hasn't been a lot of sort of attention so far, but it's created an order of magnitude change in the cost of machine vision, and maybe 2 orders of magnitude. And anytime,
or 3.
Yeah, and anytime there's that kind of a change, I mean, I've started to see it filtering out as a sensor for robots.
Right.
Are you guys not exploiting that? Is that?
Well, we are exploiting in the sense that we have the Connect SDK, and that was actually the first version of that was done in Microsoft Research, because obviously we'd done a lot of the underlying machine learning technology that went into Connect. So we did the first SDK, and then we transitioned the SDK over to the product teams, and now it's a core part of the sort of Windows proposition, as they go out to meet with new companies. And I was in Israel in April. I was amazed at the number of small startup companies that are starting to use Connect for one thing or the other.
And there were some Israeli companies that partnered with you in the development of Connect, and I was just wondering what was their role in the.
Well, there was a company called PrimeSense. There still is PrimeSense, and then they developed the sort of chip, right? That's actually doing the creating the sort of 3D field.
Okay.
But that's not really enough to make Connect work, right? Because part of the problem is first off, it's not super high resolution, and secondly, one of the traditional problems in computer vision is if all you're doing is just tracking motion, it's very easy to get confused and get behind, right? So objects occlude each other easily, and especially when you're talking about doing, 3D computer vision in a room with dancing children and dogs and and furniture and all the other things that are there. It's very easy to lose things in that space. So really, what made Connect really magical and really work, for consumers was the fact that we were able to build this machine learning system that really modeled what people did and how they were doing it and what they looked like, so that the system wasn't going to be confused. It sort of had an image of what you were doing. In some sense, it probably knew better than you did what you were going to do next. And it was able to use that to eliminate all the other errors that the tracking system would produce.
Take that technology, and what about range? I think about this when I see Google cars drive by and I see they have a $70,000 LiDAR on top, and I think that can't possibly be the commercial solution to that problem, because for one thing, the LiDARs will be stolen as soon as you park them. Can you think about a version of Connect which speaks to much greater range and works in an environment where the lighting might be chaotic?
Well, of course, Connect doesn't depend on lighting, because it's actually infrared.
Right.
Right. So the actual, so people sometimes get confused because they see the camera, and there is an RGB camera there, but the actual tracking and the recognition of what people are doing in front of the Connect is done with IR. And the reason it's done with IR is because, people play in dark rooms, right? Yeah. There's often no lighting at all. So you really had to have an illumination source in order to be able to do that. I think there are a lot of different technologies that are used for different distances, and you can either you can use light, you can use sound, you can use radar. I mean, there's a lot of different ways in which you can use these technologies, and to some extent, whenever you would do a new version of something, you're always experimenting with some really expensive piece of equipment, but if later on you figure out how to make it cheap and how to make it convenient.
So push it out. I wanted to ask you about scientific. You talked about AIDS research, and that I guess the distinction between basic science research and applied or engineering research. I mean, computer science is this funny kind of beast that it's not a pure science in the sense, and yet it's transformed every pure science. Are you shading the lab at all to doing anything as fundamental as a transistor, or you call science pure science in the sense? Do people in your lab?
Well, I mean, we're doing a lot. I think everybody has their own thing that they like to think of as pure science. I mean, we're doing very, very fundamental, basic research in computer science. You look at some of the work, for example, in our research lab in Beijing, where we've been at the leading edge of doing robust principal component analysis, where basically you take these. So historically, people tended to look at dimensionality as being a problem. Really high dimensional data. People would look at as being, how am I going to deal with that? Well, one of the things that we've been able to do in some of that work with Yi Ma is to be able to take these extremely high dimensional data, let's say video data, or oodles and gobs of web pages or whatever. Something can be represented in an extremely high dimensional space and efficiently find, coherent low dimensional subcomponents. And that's really fundamental mathematics, and yet it has huge implications on how we think about image recognition. We can now take and extract, image data out of pictures that have like 99% noise. I mean, and but it's recognizing new properties or new underlying properties of the information stream that we weren't really leveraging before. And some of these techniques now, such as robust principal component analysis, are being used in medical imagery, for example, especially doing things like MRIs for children, because children won't hold still, right? So so you produce a stream of images, and now you've got to find out that the coherent underlying image that is the bone or whatever it is you're looking for. So I think so we're doing a lot of sort of very fundamental work. The work we've done in program analysis really goes back to fundamental innovations in our understanding of type theory and how programs actually function, and and building fast theorem provers, and how you're able to do that.
I wanted to ask you particularly about your work in deep learning networks, and I also sort of wanted to see if you could frame them in the history, the evolution of neural network research. And my sense is that these deep learning networks represent sort of a third wave of neural net science, if you will. And
yeah, I'm not sure how we count waves, but certainly, I think there's been, some of our original work goes back to, there's a paper from 2009 where we're talking about using these deep neural networks as a way of dramatically improving speech recognition. We're now using that in a number of our products.
And I get the sense that you're getting really dramatic increases in performance or accuracy from these techniques compared to this kind of advances you were getting using Bayesian techniques, that this is actually meaningfully...
Yeah, that means the results we've gotten right now is we're about 30% better than anything we were able to do before, which is a huge jump for one change, for one underlying change of the technology. Although the networks take a long time to train. I think the one I was experimenting with, a more recent version that our team was doing, and they were explaining to me it took 6 months to train the models, for this particular system. It was working really well for me, but I think this is an example of, again, getting better understanding. You go back, modern sort of deep neural networks, go back to sort of 2006, 2005-ish time frame, as people started to understand, better some of the underlying mathematics for how these multi-level neural networks actually function, and could learn to tune them better, to be able to find underlying characteristics in the data.
Have we already begun to see those results in your commercial products and services?
Yeah, you're already starting to see in some of the certainly things that you'll be seeing very soon, whether it's Bing or Xbox. The speech recognition will be influenced by these new technologies. There's a technology we have called Mavis that we use for basically doing transcription and search on large amounts of video and audio that we make available as services to governments and companies out there. That's an Azure-based service, and that also uses this.
So I want to shift over to some of our audience questions because we're getting short on time. But before I go there, I want to ask you, I noticed that in what you were interviewed recently on the anniversary of the Turing's anniversary, and you got to repeatedly ask about the Turing test. But I wanted to ask a slightly different question rather than the illusion of intelligence. Given these kinds of speed-ups, what are your sort of feelings about the possibility of what's called strong AI? Do you have a view one way or the other?
I guess I would say I probably don't personally have a strong view. Having worked in clinical neurolinguistics, I'm not sure. We're a ways from understanding exactly what intelligence actually is and how to characterize it. I mean, certainly there are times when I've interacted with some bureaucrat at some agency, and I wasn't really sure I was dealing with an intelligent entity. I guess the way I would look at it is will we get these systems to the point where they are, you can interact with them in a very natural way, and they can do real things for you and help you solve problems that you have? I think the answer is yes. We're already we've made a lot of progress in that direction. Where does it go from there? I mean, I like the comment about the disaster day, which is, are the intelligent things going to take over the world or something, and eliminate us? Well, maybe, but I'm not going to hold my breath.
Let me start with this one because I know you're on or have recently joined the Anita Borg Institute board.
I think I'm actually one of the oldest members of the board.
Okay, so you've been a member for
a long time.
So This person asks, thanks for sharing, Rick. In your research center, among 850 PhDs, how many are women? Among your direct reports, how many are women? Out of how many?
Let's see. So you're asking me questions I have to do math on the fly. So roughly about 18% of our researchers are women. That's in line with the sort of national statistics that, unfortunately are falling. So if you look at the national level, the number of women getting degrees in computer science is dropping.
And do we know
right at the same time when the number of people getting degrees in computer science is going up.
Do you know why that? Do you have a theory, or is there an explanation?
I guess there are lots of things I think contribute to it. One is I think we do a really poor job in our schools, and not just for women, but for students in general, in terms of teaching them what engineering and science and computer science are really like. There's a significant effort afoot now to try to find ways to reform the system and introduce computer science into the K through 12. Brad Smith from Microsoft recently gave a speech at the Brookings Institute on that. There's a coalition of companies and organizations that seem to be focused on that and trying to come up with productive ideas for being able to have that type of an impact. But certainly I think that's part of it. I think also the field of computer science, we've not done ourselves a lot of favors in terms of the way we image and project the field, to women. I think many young women, and frankly many of their parents and their guidance counselors, don't think of computer science as a good place for a woman to be. We haven't really explained that it's a way to change the world, and we haven't really explained that it isn't just about sitting in a cubicle by yourself and programming, but in fact the modern creation of software, it is a very collaborative, very shared experience where lots of people, designers, program managers, coders, testers, everybody gets together, and works on something. So I think we need to do a better job of that. So I think those are, some of the factors, but we just need to do, we need to do a better job. And we need to do a better job of keeping women into the field once they get into the field, because that's been a problem as well. Women tend to drop out of the technology area twice as fast as men do.
There's a question that relates to that. Having attracted great talent to Microsoft, A, how do you retain, and B, how do you inspire?
Well, I think the way you retain talent is you create an environment where people really want to work. I mean, we try to create an environment where people feel like they're very productive, they have the resources that they need, there's a minimal amount of bureaucracy. So for example, one of the things that we do is we don't have budgets for research projects, right? So people don't. Yes, at some level, I have to worry about how much money Microsoft Research spends, but that's really my problem. That's not a problem that the individual researchers have to think about. If they need something, they get it. If they don't need it, they're not actually supposed to ask for it because they don't need it, right? And you want to create a sense of personal responsibility, but also a sense that you don't. This isn't what you should be thinking about. This isn't the barrier you should be concerned about. You should be worrying about coming up with great ideas or pushing the state of the art in your area or finding the weak point in that intellectual frontier. You shouldn't be worried about how much it's going to cost. We'll figure out how to pay you and how to pay for the things that you need.
To that point, last week I was on Microsoft's West Campus, which didn't exist the last time I was at Microsoft, actually. And this is based on one morning's wandering around. So, traditionally I felt that Microsoft was a little bit, so it didn't have the flavor of a Google, of any particular Silicon Valley company that was on a roll, the Silicon Valley company of the moment. But this campus, I thought, had that kind of a feeling of being all-inclusive and being, full of activity and being sort of opulent, too, in a sense. And was that intentional? Have you done something different on the West Campus to make it a really great place to work?
Well, I think in general, Microsoft has worked really hard over the last few years to, do a wide variety of things that really improve life for employees. So, both we've upgraded facilities on the campus. We've made it, there's that's not always, just altruistic. If people can get, things done on campus, then they don't leave, right? They keep working. They go back to their offices afterwards, get your hair cut, and then go back to your office, right? So there's that aspect. But we've done things too. We created the connector bus system, that goes now all the way through the Puget Sound area. So we have these Wi-Fi equipped buses that bring people in from Seattle and Duval and Woodinville and Federal Way and so forth. And that's been a huge improvement, especially for a lot of younger, new employees that maybe don't have enough money to live close to campus. Right. So, they're going to find better housing elsewhere, but now they have an easy way to get into campus, and they've got access to Wi-Fi and other services while they're traveling, so they don't have to feel disconnected.
Is there that San Francisco Peninsula thing where the young hip people all live in Seattle and Belltown, and they like to?
I think people are pretty distributed. I mean, I certainly know a bunch of people that do love living in the city, and there are of course different districts that have different flavors in Seattle, and I think that's part of the charm of Seattle. And then I know people that like living out in the country. They like living up in Woodinville or in Duval, Monroe, where these are really more like out in the middle of the country, and there's cows and horses and things like that. So. Yeah.
Here's a question. How can we motivate youngsters to take the DIY approach your generation did? Your people are I'm having trouble. More people are consumers today than producers. So how can we create a hobbyist class of
the interesting part about that is I'm not sure that's true. I see, when I go visit, maybe I certainly see probably a slightly different group of young people than everybody else does. But I go into high schools, or I see students in various kinds of competitions or in various kinds of programs, and I'm just amazed at how much stuff these kids do. I mean, a lot of kids are learning to program at 6, 7, and 8. They're experienced in writing software by the time they're in high school. Many of them run their own websites. They develop applications that they put out on different app stores or on the web. I think it's always one of these things where everybody has this nostalgic view of the past, right? It's like the golden age. Everybody's always talking about the golden age of the Greeks. It really wasn't that great. Okay. They had a lot of problems back then. Plumbing being one of the principal ones. But I think that it's what I see is just a lot of incredible young people. We have this program at Microsoft Research in Redmond where we actually bring in about a couple of dozen high school kids as interns. We started that a few years ago, and I am just amazed at what these kids do. And I didn't ever meet any kid that smart when I was a youngster. I'm just amazed at how much these kids are doing. So I think we've in some sense we've created a world in which people can in some sense produce, but they do it differently. They don't tinker with cars that much, right? It's a different kind of do it yourself. They tinker with websites. They tinker with, they manipulate JavaScript. They go in and develop, little applications for themselves. And it's still not, these aren't huge numbers, but they never were huge numbers, right? Yeah.
So here's a computer science question. Looking ahead, what are the most important areas of computer science for Microsoft to be the best in the world? And then in parentheses, don't say, quote, all, unquote.
Why not? Well, certainly my goal is if we're going to be doing research in an area, we should be at the state of the art. If you look at today, Microsoft Research is the number one publisher of basic research in the field of computer science. I think of what we do as really being, pushing the state of the art in all these different areas. I'm just trying to think. I can't think of a good way to pick, winners and losers, out of that space. There's a lot of things that are really important. Obviously, there's a lot of progress being made right now in machine learning. That's a critical technology. It's an area that we've been making pretty heavy investments in now for a very long time, and I think they're really starting to pay off in a significant way. But as I said before, some of the investments we've made in, program analysis or investments that we've made in fundamental mathematics or signal processing, those are also paying off in really significant ways too. And often you don't realize how something like that's going to pay off until it really does, right? I mean, one of the sort of good things and bad things about basic research is that, you don't necessarily have a plan for what you're trying to do. You're constantly exploring, you're thinking of ideas, you're pushing, in any place that you can that looks like it's going to give, on that frontier. And when you do that, surprising things come out. And sometimes you don't know that they're really that interesting until 3 or 4 years later. And then sometimes things that look really promising right now turn out to be nothing 3 or 4 years from now. Because there's some hidden flaw that you didn't see right away. So I think it's this willingness to be sort of invested not so much in ideas, but in people, right? Because people are the things that are going to produce the steady stream of new ideas. And I don't try to manage technologies. I don't try to manage what we do. I just try to make sure that we have the best people we have, and that they're as productive as they can be, and that and then I'm giving them a way to sort of realize whatever their dream is, within their space.
Let me ask a final question. So your lab, Microsoft Research, has done very interesting research in a problem I guess is described as dark silicon. We are reaching fundamental limits where you can't keep all the switches on a modern piece of silicon active at the same time because of fundamental limits in heat, the heat that's produced. Where are you on the limits? Where are we in Moore's law? Is the party as close to being over as some of the doomsayers say, or are we simply going to shift technologies and keep moving at the same pace?
So I guess I've always had the belief that Moore's law is more about us than it is about computers. It's about the fundamental belief that we've had in the technology field for some time now, that we can keep solving ever greater and ever harder problems, and we keep coming up with some new way to do it. If you look at what we're doing today, we're building these enormous data centers. We're collecting, astronomical amounts of petabytes of data. And we're extracting information from that data that is helping us solve fundamental problems, whether that be environmental issues, health problems, really coming into sort of fundamental understandings of things like how speech recognition really works or how computer vision works. And so in that sense, I think we're going to keep moving forward. Individual technologies are going to come and go. And they have for some period of time. I mean, at some point, we're all going to be standing around saying, electricity, how quaint, oh, nobody does anything with electricity anymore. I mean, I think that's kind of the way I think the future is going to be. If we get stuck someplace, we'll find another way. We'll find a way around it. Not because the technology allows us to do it, but because we choose to do it.
I've asked about a third of the questions I wanted to ask, but we're out of time. Thank you very much for taking the time.